All right, so part of the whole idea behind this section that we're doing is being able to prove triangles are similar. Right? So we already learned that there are 3 ways to prove triangles are similar. What are those 3? The 3 postulates that we can use to say this triangle is similar to that triangle. Give me one. SSS similarity. Right? Now we had learned SSS congruence, now this is SSS similarity. So sides have to be what to each other? Proportional. Good. AA similarity, which means 2 pairs of corresponding angles are what to each other? Congruent, right? And then what's the last one? Yep. SAS similarity. So those are our 3 choices. I'm sure you knew that it was coming that you had to use these in proofs, right? Of course. So that's what we're going to practice a little bit today. Just using those, and what does that look like in a proof? It is very, very similar to triangle congruence proofs, right? There's a lot of likenesses. But the big difference between triangle congruence and triangle similarity is that the sides are proportional, not congruent. So that looks a little different when you see it in a proof. Okay, so obviously we always label our diagram first. Now, let's do this first one. Given PQ is perpendicular to QT, and ST is perpendicular to TQ, and PQ is to ST as QR is to TV. Now, when we go to label our diagram, you might want to draw these separately. Label the right angles. Now, remember, when you have a proportion like this, we have that little squiggle method, right? We can label the sides. PQ is to ST as QR, double squiggle, is to TV, double squiggle. Which postulate do you think we're going to use to say these triangles are similar? SAS looks like, right? We have 2 sides and the angle between them. Now, look at what we're trying to prove. We're trying to prove that VKR, this one in here, is isosceles. So that's a little weird, right? But I promised you that first we should prove the triangle's similar. Prove the triangle similar first, and then I'm going to kind of teach you what comes beyond. Just warning you, don't write too big in this space. This proof takes up a little bit more space than you might think. Okay, so we're going to start with PQ perpendicular to QT and ST perpendicular to TQ. What's the conclusion that do you think we should make from these statements? What conclusion can we make from the perpendicular statements? Yeah, Ryan. Okay, so PQ perpendicular to QT, we could say angle Q is a right angle. ST perpendicular to TQ, we could say angle T is a right angle. What's the reason? Good, definition of perpendicular. In order to use SAS similarity, which is what we decided we were going to use, right? We have to have 2 sides, 2 pairs of sides that we know are proportional, and 1 pair of angles that is congruent. So the step we need to take from here is to say that these 2 angles are, yep, good. So angle Q is congruent to angle T by the right angles theorem, or all right angles are congruent. Now, you may think SAS. Seems like we should have three arrows pointing to our box that says the triangles are similar, S, A, and S. But that was true with triangle congruence, right? But the difference here is that both S's, it's not working. Okay, both S's come from this one box. Right? There are two pairs of sides, all in that one box. We were able to take that one given and mark all these squiggles. So it's actually only one arrow from that box that takes into account both S's. And then an arrow from here. Now we can say the triangles are similar. P, Q, R, similar to triangle T, nope, sorry, S, T, V. SAS similarity. So now we have a problem. We're trying to prove that this VKR triangle is isosceles. How could we possibly prove that that triangle is isosceles? What needs to be true for it to be isosceles? Yeah, Jane. Okay, so the idea was to mark angle R and angle V congruent, is that what you said? Right. R and V congruent. What might be a logical reason why we could say those are congruent? Yep, Andrew? Think about what we've proven in this proof so far. So far we've determined that these two triangles are similar. What does that mean? If we know the triangles are similar, what does that mean? Brett? Yeah, the definition of similar triangles says that corresponding angles are congruent and corresponding sides are, what's that P word? Proportional, right? So corresponding angles are congruent, corresponding sides are proportional. So remember back when we proved triangles congruent and we said we could go that one more step? It was like CP/CTC or definition of congruent triangles, right? We said we've used 3 parts from each triangle to prove these triangles are congruent, but there's still 3 remaining parts. Once we know the triangles are congruent, we know those other parts are congruent, so we can use that. Same thing going on here. Once we know the triangles are similar, you can use that fact to say, oh, well, these other angles I haven't mentioned yet, they must be congruent too. And these other sides I haven't mentioned yet, they must be proportional too. So, if we go with the idea of saying angle, R is congruent to angle V, just because those triangles are similar means that all of the corresponding angles have to be congruent. So this is going to be, like you said, definition of similar triangles. Just like we did definition of congruent triangles before. Well, if R is congruent to V, in our original diagram here, that's these two angles. Do you see how that might help us to say that that little triangle is isosceles? What would we have to say next? Can I go straight to saying they're isosceles? That it's isosceles? What do we have to say first? Segment VK congruent to segment RK. Reason? Exactly. Converse of isosceles triangle theorem. Right? If the angles are congruent, then the sides across from them are congruent. Therefore, we can say this is isosceles. Triangle VKR is isosceles. Reason? What's the reason? Definition of isosceles, right? By the way, there will never, ever, 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 ever be a reason that contains the word definition and theorem. Something is either a definition or it's a theorem. I've been seeing lately people write like definition of the isosceles triangle theorem. No such thing. Okay? It's either a definition or it's a theorem, or it's a postulate, or it's a property, or it's something else. But those are all mutually exclusive items there. Yeah. All right, so let's look at this next proof. Hopefully yours didn't come down as low as mine did there, but this proof we have AB parallel to CD and BC parallel to DG. And we're trying to prove this weird looking thing, which I'm going to get to later. But I promise you, first you want to prove the triangles are similar. So, which postulate do you think we're going to use to prove triangles similar based on what we're given here? AA similarity, exactly. What kind of angle pairs do you see here related to those parallel lines? Corresponding angles, yep, good. Okay, so since AB is parallel to CD, which angles are congruent by corresponding angles theorem? Which two angles? Based on those two parallel lines, which two angles would be congruent? Yeah. Good. Very good. Angle A congruent to angle DCG. Now remember, it's okay to call it angle A because that angle only has one angle at the vertex A, but you can't call the other one angle C because there's too many angles that have C as a vertex in this diagram. All right, because BC is parallel to DG, which two angles would be congruent? Which two angles? Angle G and angle BCA. Good. Again, corresponding angles theorem. Are we ready to say the triangles are similar? Yes, we are. By AA, we just need two arrows again because two angles is enough. So triangle ABC is similar to triangle CDG by AA similarity. Okay, so we have the triangles similar by AA. Remember, after you've proven the triangle similar, there's that next step that is sort of reminiscent of CPC-TC type thing, right? Once you prove the triangle is similar, you could either say sides are proportional or angles are congruent. The remaining sides, remaining angles. Now, there's only two choices of what that next step could look like. Either an angle congruent to an angle, or a statement that looks kind of like this, right? That would be saying sides are proportional. So the next step after triangles being similar is either going to be, oh, this angle is congruent to that angle, or some proportion showing that sides are proportional. What we are going to do is write a proportion that involves, look at our proof here, that involves these sides. Side AB, that's this one. Side CG, that's this one. Side CD, that's this one. And side AC, that's this one. Those are the four sides that we want to involve. And we're going to write a proportion using those sides. So if I say AB is to, what would I put underneath that? CD, good, right? Because that's like the left side to the left side, equals, what should I have on top here? AC, because that comes from the same triangle as AB, right? We got that on top, over CG. That is what your statement looks like when you're trying to say, oh, since these triangles are similar, the sides are proportional. What do you suppose our reason is here? Definition of similar triangles. Definition of similar triangles. Now, that's not exactly what it said to prove. It said to prove AB times CG equals CD times AC. Why can we make that next step from here? Why is it true that AB times CG equals AC times CD? Why is that true? Yeah. Yeah, because you're going to cross multiply. Exactly. AB times CG equals CD times AC. That's what we're trying to prove. The reason I'm going to have you right there, either cross products are equal, or that's called the cross products property. Okay, so this is one way you could have done this proof. Did anybody use a different way? Yeah, Andrew? Yeah, you could have done just one pair of these alternate interior angles and used vertical angles instead. Angle GIH congruent to angle KIJ, vertical angles theorem, and then AA. So that's another option. I could have used one pair of alternate interior and one pair of vertical, or two pairs of alternate interior. Then you prove the triangles are similar by AA. Only one extra step here. That proportion is a step that can come directly from similar triangles by definition. Any questions? Okay, in this last proof here, which we're not going to do right now, I want you to change this to an angle symbol and an angle symbol and the word angles instead of triangles.